Uh, it's great that we're organizing something across several countries in the Mediterranean and South Europe. I hope we will do more of this kind of collaborative training events. I just want to tell you a few things about us in case you don't know about the Cyprus Institute. So, of course, we are here in the island state of Cyprus, and the Cyprus Institute is basically a research and educational institution in Cyprus. It's a non-profit, non-governmental organization, and it has been around for more than 15 years, actually. We are organized in a number of different research centers. We have a research center for energy, water. We have another research center for climate change, another one for public policy. We have one for digital cultural heritage. And finally, one for computational science. And we are based on that research center. So that research center is called Castor C, Computation-Based Science and Technology Research Center. We're basically a group of about 6 or 7 faculty members. We have a research staff of about 30 people. We also have masters and PhD students, and we're working on areas that relate mostly with machine learning, multi-ligand simulation, HPC. Recently, we started an ERA chair project in quantum computing. So these are the main research areas of Castor C. And here I'm just showing you the various methods that we often use in both our research papers and also our research and development projects. We're working on a number of applications for either industry projects or working with the government or working for research grants, Horizon Europe or national research grants. Some of them relate with computer vision, others with modeling of materials, helping the climate scientists with machine learning methods. We have projects in smart farming, and of course in using machine learning in medical imaging and health. The Research Center Castor C is also the National Competence Center in HPC in Cyprus. We're operating a number of clusters. The cluster that is open for every scientist in Cyprus is called Cyclone. It's an old machine, but now we're in the process actually of getting a new machine. And I should also say something that is still very recent, that we are also coordinating the AI factory antenna of Cyprus, the project that is called Pharos Cyprus. So if you are involved with AI factories, we will definitely see you at those meetings. I just want to show you not the entire, of course, research center, but these are the people that are working with me mostly in machine learning AI. And this is just an overview of projects that we have either from the national funding agency called RIF or from Horizon Europe. And of course, if you are interested in collaborating more in any of what you have heard, either research projects or doing training events together or any other form of collaboration, we're very open to working with you. So you can reach us at this email address. And thank you very much for being here. I'm sure it will be a very interesting training event, and I will not take any more of your time so that you can actually talk about LLMs and applications in different areas. Thank you very much.
Thank you, Constantino. Welcome everyone again from my side as well. We will start with Luca and Andrea from NCC Italy. The presentation will be about Victoria, your private AI. Guys, who is going to be presenting?
Yes, let me see if I can share the screen. Okay, I have the same problem of the presenter view, but let's see if I can do it like this. You should be able, okay, to see.
Okay, we can see your slides.
Okay, so hello everyone. My name is Luca Babetto, work in Cineca. And today I will, alongside my former colleague Andrea Proia, talk to you about Victoria, the service that we have developed for EuroCC Italy that enables everyone from small and medium enterprises to large companies to deploy their own private AI chatbot for internal documentation. First of all, a quick word about our partners for the Italian NCC. I'm here representing Cineca. We host we're an HPC center. We host the Leonardo supercomputer that to this day is still the 10th in the 10th position in the top 500 list. We have collaborated on this specific project with Leonardo SPA, company dedicated to aerospace, defense, and cybersecurity, and who have sponsored the scholarship that Andrea has used to help us develop this project. We also work with Dompé Pharmaceuticals, another company, a large company invested in research for HPC and AI on the pharmaceutical side. And also IFAB and Virex, there are two companies that are helping us, especially with the training and dissemination for technology transfer for small and medium enterprises, especially. So the agenda today, I will let Andrea talk about the specifics of Victoria, as he was actually the main developer, one of the main developers of this project. He will talk briefly about LLM fine-tuning and RAG, which is a technology that we have implemented in Victoria, and explain a bit about the Victoria workflow specifically. Then I will show a brief use case on some answers that use different LLMs and how they compare to each other, and finally a brief showcase on how to actually deploy this system and to show you how easy and simple it can be. So okay, I'll leave the floor now to Andrea.
Okay, so hi everyone, and thanks Luca for the introduction. So let's go with the agenda, but before starting with explaining what actually Victoria is, so a retrieval augmented generation pipeline, why we may need this kind of technology, we first need to understand a bit of a comparison with a fine-tuning operation, which I'm sure you know, which may be a solution in case you want to specialize your LLM on your private specific documentation. So let's say we want to specialize our model with our private document. What we may do is to perform a fine-tuning operation, which is just an additional training step that we do on top of a already pre-trained large language model that we can download open source from the web. And by doing so, we are injecting actually the knowledge inside our documents inside the parameter of the neural network. So we are updating those parameters to obtain a specialized model. Instead, the RAG technology, which is exactly this slide, is a technique for retrieving relevant information from an external source, because the fine-tuning operation, sometimes may have some high related costs in terms of computational power and also money. So a RAG pipeline may help us in avoiding these costs. So in this case, we are not injecting anything inside the large language model, so the model remains untouched, but we are just attaching an external source, an external knowledge base to the LLM, and we use this information, parts of this external knowledge base, as input along with the query to help the LLM to answer to the user question. Let's see in the next slide a direct comparison between the fine-tuning and the RAG operation to see why we decided to use this kind of technology. So on one side we have the fine-tuning operation, which as a pro, as that it gives us a specialized model, which is totally fine, but it also carries high computational costs from the point of view of the power that we need to do such operation. And most importantly, this operation must be repeated every time the documentation changes, because if we want to update with further documentation, we need to perform an additional fine-tuning operation. And also we need usually a quite big and high quality dataset to perform this operation in the correct manner. On the other side, the RAG does not give us a specialized model, but we still rely on a general purpose model that we can download open source. But this is totally fine because we are injecting the knowledge using our ecosystem. So we are helping the generic purpose model. But the pros are that we contain the computational cost because we don't need to perform any training step on the LLM. We can modify the documentation as many times as we want, because we can just attach different knowledge bases to our LLM as we need. And also, this is an important part, we reduce the probability of hallucination, which is a phenomenon that, you know, it may happen with the LLMs, because since they are just autoregressive models, they produce the next most probable token in a sequence. And so sometimes they tend to produce fake answers that are not grounded with our actual documentation. So in the next slide, we start looking at the first of the two workflows that we have inside Vectoria, and actually inside any RAG system. The first one is the index creation. So we have our documents and we want to obtain the external knowledge base that we mentioned before. So we start with the documents. We need to clean them in order to remove all the noise and to have just the information inside the actual content of the documents. And then we need to split them into manageable portions of text, which are called chunks. Each of these chunks, the blue ones that you see, is then embedded. This operation is done by a specific kind of neural network, which is called an embedder, as you can imagine. And this network just converts this portion of text into a vector of float numbers with a fixed size that should, should represent the information inside the text of each chunk. So we have a one-to-one correspondence between a textual chunk and its embedding, which is a vector of number. Each of these vector is then stored inside a vector database, which is a specific kind of vector that is used for the second workflow to perform the similarity search. Yeah, and here we have how we actually answer to the user query using the retrieval and the generation part. This is why we have a retrieval augmented generation as an acronym. So everything starts with a user question that you can see on the right in green is embedded using the same embedder that we used before for every chunk of our documentation. And then with this embedding of the query, we performed a so-called similarity search inside the vector database, which is an operation done to retrieve the most semantically similar chunks with respect to our query. And here we retrieve the top k chunks where k is an hyperparameter that we can set as we need. And hopefully these chunks also contain some information that is useful to answer to the question, since they are the most semantically similar to our question. So we pass the user query and the chunks that we retrieved along with the instruction to form a contextualized prompt, and we pass everything as input to the LLM that is now able to hopefully give us an answer which is grounded using our documentation. So the vector search is not magic, it's just a mathematical operation under the hood, because as you see, we have a question, we embed the question, and then we search inside the vector database for the most semantically similar points. And we do so by just performing an operation like a cosine similarity between vectors. And as you can see on the right, in this case, we are, as an example, retrieving the top 3 chunks. And we were lucky because one of these documents also actually contain some information that can be used to answer the query, which is what are the steps involved in handling purchase requests. So all these chunks are then aggregated together to form a reference for the LLM. Victoria is not just a matter of code, but we need to involve people. Because first of all, we need to activate the right stakeholders to get the documentation of our company, because everything starts with the documentation. Then we need to study and pre-process the documentation to extract the metadata. If possible, it is not mandatory, but it helps the filtering operation inside our knowledge base that may be also very large. And then the third point, which is the most important, is that we need to get question-answer pairs, so a test set from domain experts to test our system, because since this is AI, but we want to be sure that the system is behaving in the intended manner, and so it's producing the correct answers. And now I leave the floor to Luca, which will explain you how to scale and deploy Victoria on HPC.
Yeah, I want to further stress this last point that during the development of Victoria, we didn't use let's say, a standardized evaluation system, but rather we focused on getting some answers and question pairs from actual domain experts within the context that the RAG workflow had to extract information from. And actually in Leonardo, they are actually implementing this system in their own business management system for production use. So, and I will show you a quick showcase on a few test sample answer question pairs that we have performed on 3 different systems. One of the strong points about this workflow is that it is scalable and transferable, meaning that it works from, of course, HPC clusters with lots of GPU memory. And for this test, we have used we employed the Llama family of LLMs. And for the largest one, we used the 70 billion model that fits in a single node of Leonardo. We have also tested smaller systems, one that should fit in any high-end workstation with a single GPU with reasonable amount of memory, so the 8 billion, and as well as, say, trying to break the system also on a laptop CPU, so not even GPU accelerated, with the smallest model available from Llama family, the 1 billion model. As a first test, we created the vector database on HPC, and this was also actually used for all runs, meaning that it is also possible, for example, to use HPC not just for the vector database and inference, but you can also produce the vector database if you have a lot of documentation on HPC using high computing resources, and then transfer that database to a smaller LLM that you can run on a scaled down system. I downloaded the AWS documentation, which is 8 PDF files for about 20,000 pages. Obviously, since it's a pretty famous service, we're not actually sure if this was also part of the training dataset, and we've done a second test to also account for that. And I just asked a couple of questions to see how the model behaves. For some questions, we can actually see that the smaller systems, the smaller models may actually be a bit too limited, but also going from just a regular workstation, we can see that we start to get similar answers and perfectly satisfactory answers. Obviously, the larger model reads a bit more natural and is a bit more conversational, but the content of the answer was satisfactory for both, and both were able to actually find the correct piece of context for this specific question. Oh, I forgot to mention that for the largest model, we are also employing a re-ranker stage. So after the search for the context relative to the answering question, there's also a step that is specific to re-ranking the chunks and help produce better ranking on this side. For the second question that I asked, actually the smallest model was able to produce a brief question, but with the correct content for that we needed. Again, as you go higher in dimensions, obviously you get the more accurate and elaborate responses, but this is expected. To see if how it behaves with surely not seen before documentation, I've also compiled a list of some scientific papers taken from the Open RAG benchmark dataset, which is comprised of about 400 positive documents, meaning that the list of questions that they wrote was linked to one of these specific documents, but also featuring 600 completely unrelated documents to try and distract the pipeline and make some introduce some noise. These are all very recent papers, so it is very unlikely that this was seen during training. So we should have a pretty blank slate to test this this comparison. Once again, the vector database was compiled on HPC, and that file was transferred, was copied to all other machines without needing to rebuild it from scratch. This specific question, we see that the smallest model was actually able to find the correct document because it started to give the correct answer, but it stopped at some point, probably because the capabilities of this model were a bit too limited. Still, it's interesting to see that we see that it found the correct document to evaluate, and once again we see that the larger models are able to produce the correct answers. And on this question, we see that actually, despite being able to find the correct document, there is a subtle nuance on the answers that make it so that the smaller models, even the 8 billion, is not quite correct in the answer, while only the largest model was able to appreciate the subtle differences that were necessary for the correct answer. And this is once again the reason why it's very important to have domain expert validate the answers that the models reproduce. And as a third test, we see that sometimes the model is completely incapable of producing basically any answer. It just outputs a point, a dot, while the others have similar answers. So even with a high-end workstation or a small instance in a small cluster, companies should be able to feature a RAG workflow, which is by this nature completely private, because you're not renting any compute time on AWS or some third-party hosts, or using a third-party AI. And so companies are able to protect their intellectual properties and data this way. The deployment procedure is very simple and straightforward. We use an Ansible workflow for the deployment, which can be cloned by just downloading the GitHub repository, which you can find at this link. It's completely open and free to download. And you only need to edit 2 files for the deploying procedure. A host file, which just you need to input the IP address or the address of the machine where you want to perform the deployment, and the username to use. Obviously, you should have your machine should have SSH access to this machine. And we condense all the relevant configurations in a single file, where you can tell it where to install the Vectoria. Optionally, since during the download of the LLMs, many of them use the Git LFS. Also, if you have some modules that you would like to preload on HPC for the virtual environment of choice, some configuration about the job scripts that will be created by the deployment procedure, with the account partition, how many CPUs and GPUs you have access to, and some specific LLM settings, so the language in which the documents will be found. Currently, we support Italian and English, and the format, which can be PDF or Word documents. And also, all this configuration can be adjusted at a later time, but for the defaults, you can also tell it to use quantization for both the re-ranking and inference stage. This is possible to do also locally. So if you want to install Victoria on your local machine, you just have to, in the deploy configuration file, to change the host to your local host, and all the procedure that I will show here also happens locally. For the deployment, you just have to run the single command, and then the Ansible playbook will take care of everything. So loading and reading the configuration that you have provided, creating the necessary directories, either locally or on the remote host that you have indicated, installing the Vectoria code base on HPC in a Python virtual environment that is configured as you have requested. Here it's writing the sample, the template script files that you can use to launch on HPC with pre-made configurations that should be ready to launch as they are, once you just have uploaded the documents that you want to run the your RAG procedure on. And here it's also taking care of downloading the LLM, the embedded, the re-ranker, and the inference engine that you have requested. Just one point of caution: some models, like the Llama family of models, require you also to register your SSH key on Hugging Face for the download. So as long as you've made sure that you can download these models on your machine, it should be able to automate also this procedure. And after this stage, the system is ready to use. So to reassume on the conclusions, what Vectoria enables the industry to do is to provide a RAG workflow which is fully private and closed. So again, without needing to sign up for ChatGPT or the various Copilot alternatives, everything is used on premise, and the company has the full control on everything that happens. There is nothing leaving the infrastructure. The deployment is very simple, so it's streamlined with Ansible. Just a few commands can get you up and running straight away, also leaving the option to customize a configure for the expert in the sector, all the various scripts that are produced. We have multi-format support for PDF and Words, also for currently English and Italian, 2 languages. It's highly customizable and scalable, so you can fully scale from personal laptop without a GPU to HPC facilities and anything in between. So it's very flexible and customizable, and obviously it's fully open source. So all the components and the code base are completely open and free for anyone to utilize and download. Thank you for listening. I don't know if we have time for some Q&A or if it's left at a later time. Of course, for any question, you can reach out to us personally, and we'll be happy to get in contact.
Hi, thank you, Luca and Andrea. Maybe one quick question from Nikos, and then we can have some time at the end of the session to ask more.
Absolutely.
Okay, hi, it's Nikos from NCC Greece. Thank you very much for the very interesting presentation. Okay, I have noted many questions actually because I found the presentation quite interesting, but I understand that we don't have time now. So I will just ask about the vector database, if you have any information about the size and how many vectors you produced, any scaling issues, etc.
Andrea, I don't know if you want.
I noted it was 20,000 pages.
Yes. So, okay, I can say that for the AWS, the index is 400 megabytes for the AWS one was about 430 megabytes for the VectorDB. The other one, since it had few less documents, is like 40 megabytes. So we're in the order of like half a gigabyte for 20,000 pages of PDFs. I don't know how this scales with different documents or formats, but roughly this is the ballpark, let's say.
Okay, I understand something very fast. The deployment was on Leonardo. You said that, how the authentication works. I mean, you need to authenticate with you do SSH to when you serve the model.
Yes, the Ansible script is run locally on your machine. If your machine has SSH access to the host that you want to do the deployment on, that's enough. So as long as you have SSH access to Leonardo, you can do the deployment on Leonardo.
Nice. Thank you very much.
Great, thank you. Now let's proceed with Professor Yannis Christou.
Hello.
Hello.
Let's share my screen. And okay, so hopefully you can see my screen, guys, and now the slides in presentation mode.
Yes.
Okay, great. So my name is Yannis Christou. I'm an associate professor at the American College of Greece, together with Nikos Bakas, we're from NCC Greece. And I will present research work that we did for ESA last year between late 2023 and October of 24 on developing LLMs for satellite communication knowledge management for the European Space Agency. And of course, this is joint work with Alessandro Mocho, Sergio Rojas, Francisco Valverde from the University of Malaga at Spain, Dimitris Voyagis, a colleague of ours at ACG, and Thomas Navarro at the ESA. So I will give you an overview of the problem and some related work. Then I will describe the knowledge extraction process, which, as you shall see, has a lot in common with what Luca and Andrea already presented. And then I will, instead of discussing a RAG process, I will discuss a fine-tuning process that we followed so as to have an on-premise model that can act at the same level of accuracy as the large public models, at least, let's say, ChatGPT 3.5 or maybe 4. I will finish with an evaluation of the fine-tuning models that we created, results, and then some key takeaways and future directions. So, as the previous speakers very nicely put it, applying large language models to niche fields is something very important, has many benefits. It also presents unique challenges. One can easily see that even the largest trillion parameter models that we see today from ChatGPT 4 or 5 or the Gemini models, still they are not performing at the expert level in certain fields for which there are not many related data in their training set, or if they have not been fine-tuned via HFRL in their post-training phase. Satellite communication in particular encompasses a wide range of technical detail protocols and operational guidelines that a model needs to be, a large language model that is, needs to be trained on specifically in order to produce good results in practice. For reasons of privacy and data security, which were major requirements in this particular call for projects that we responded to from the ESA, it was the SatNex 5 project, we are only investigating on-premise models and their performance. So, we have worked with two major models that were already, well, one of them was mostly mentioned in the previous talk. It was a Llama Instruct model version 3 with 8 billion parameters, as well as the Mistral Instruct model, 7 billion parameters. Now, these models, of course, need some server to be embedded with so that they can then respond to user queries via some protocol like HTTP, etc. So there are a number of on-premise deployment tools like Ollama, the Anything LLM server. Of course, the VLLM server that a couple of years ago was touted as a very nice server that could speed up operations, even concurrent requests on the same server and the same model. And of course, the LM Studio, which offers a kind of an integrated development environment, together, of course, with an embedded server to which once you have loaded up a model, it can be used to serve the model inference. So you can see here on this on this table that I'm showing you how the various tools and the various servers feature in terms of platform purpose, model support, user interface capabilities, deployment options for various LLMs, integration features, security and privacy features, and finally, how much scalable each solution is. At the beginning, we started with LM Studio because it was quite easy to work with. Eventually, we switched to Ollama and Anything LLM. For VLLM, for the particular hardware that we had available, we found it back then, at least last year, it was relatively unstable for anything other than very small size models. So we did not end up using it. Now, the knowledge extraction process is very much the same whether you are doing retrieval augmented generation or fine-tuning, especially when you have to work with large PDF documents. The key challenges in PDF content extraction is about the nonlinear layouts of PDF pages, mixed content types used within a single document, header, footer, noise in those areas, and of course the non-textual elements that might be included, which of course make absolute sense from a visual perspective to humans, but they are not. They make the work of extraction tools much harder. We ended up coming up with a cleaning pipeline that involved text extraction using any of the tools that you see at the top right of this slide. Removal of irrelevant content, deduplication of content that may appear more than once or may be very, very similar. For example, in a legend of an image, of a figure or a table. Taking care of ethical considerations, even though in this particular project that we were, where all the documents were taken directly from the ESA website, so there wasn't any content that could be considered offensive to certain groups of people or to ethical values, etc. And then finally, we follow the normalization procedure to create the final content. Table handling is always an issue in document extraction, in knowledge extraction from documents, whether it is PDFs or if it is pure text, right? Here, the table handling was an absolute necessity because there are many issues to be found, as we discovered when we are trying to extract knowledge from the PDF documents of the ESA. We found one particular tool, Camelot, to outperform both Tabula as well as Acrobat in this process. And this is why, we used it to do most of the table handling. Improvements we were able to obtain included filtering out tables in headers and footers, as well as eliminating any overlapping text fragments within the documents or the cells in the documents. Next comes the fine-tuning phase, where the data set that we have obtained is used to actually change the parameters, as the previous speaker said, of the LLM. For doing this, we used low rank adaptation, so as not to have to spend too much time changing all the parameters of these 7 or 8 billion parameter models. And we also used the SFT trainer model from Hugging Face. After that, we perform model merging and quantization, of course, because even though we actually ended up with one particular model that we did not quantize at all, but we kept the full model and all the accuracy that we had for every parameter. And the final step is to prepare the conversion of the parameter files to a GGAF model file, so as to be able to give it to the servers that we mentioned before to serve the model directly, for example, via LM Studio or anything LLM and the rest, right? Now, you can see the single machine that we used to do this fine-tuning on the left, on the lower left of the slide. It is a Linux server that we are full administrators of it. We installed directly on the Iron Ubuntu Linux 22.04, the long-term support release. The machine has one AMD EPIC CPU with 32 cores running at almost 4 gigahertz. It also has a single NVIDIA L40 GPU with 48 gigabyte of video RAM, which turned out to be enough to do the fine-tuning that we wanted in approximately 8 hours. We provided a cutoff time of 8 hours for each of our fine-tuning runs to see how the models actually perform after this relatively small runtime in a low-end server. By the way, this server is a micro server. I forget the name of the company that makes these servers, but I do remember the cost. It cost together with VAT. It was a 15,000 euro machine. So it's a rather cheap machine, which is of course extendable. It can get another three GPUs. And one more same AMD EPIC Genoa CPU. The total RAM memory can be expanded to like 2 terabytes, and there are enough slots for SSDs, of course. So basically, the fine-tuning process took place on our data set, which comprises of approximately, if I remember correctly, 5 gigabytes of text extracted from the documents, from the publicly available PDFs of the ESA website. And we also developed, with the help of one of our students at the American College of Greece, Mr. Hastoukis, we developed a web app in order to facilitate with user-to-model interaction. So besides the server, the Olama or the LM Studio or the anything LLM server that actually serves the model, we have a web server that is based on the Django framework, Python framework for developing web apps, which actually serves web pages to the browser of a user, who can then in turn actually send directly queries to the web app, and the web app sends these queries to the model server, gets back gets back the responses and serves them back to the user. The web app also has the ability to perform RAG if needed, even though we didn't do anything like that, and has a number of other capabilities. Here you can just see a couple of screenshots that showcase some of the functionalities of our web app. The major functionalities is to register users, to manage them, to communicate, of course, with the server hosting the large language model. We have the ability to swap LLM servers at the runtime. If the user doesn't like a response from one model, they can swap to another model if we had one, and a corresponding server. It manages user chat history, and it allows for RAG operations, as I already mentioned. The overall process workflow looks like this data flow diagram that you see on the right of this slide. So from the original data set of PDF that we scraped from the ESA website, we perform text extraction as well as table content extraction via the use of the Camelot framework. This follows the pre-processing phase. This is fed as input to the pre-processing phase that I mentioned. And then we actually went ahead and tried two different approaches to fine-tuning. The first was to provide the data set, this extracted text as it was, as input to the fine-tuning process. So essentially provide it as essentially document completion, right, to the LoRa. And the second was to first create question-answer pairs, which could allow the data set that is given as fine-tuning material to the LoRa process much closer to the question answers that we wanted to make the system learn, right? So whereas the first attempt just gives the entire extracted text as further training material, the second attempt actually generates a set of question-answer pairs using, in fact, a large language model, and then proceeding to the fine-tuning phase. And after that, we performed, actually our colleagues at the University of Malaga performed the evaluation phase, where we are using yet another LLM as a judge, and we we compute some custom factual metrics. So the response, the results, as you can see here, are relatively, from the first attempt, are relatively disappointing in the sense that the fine-tuned models, both Llama and Mistral, actually perform slightly worse, and in fact, in some cases, quite worse than the non-fine-tuned models, right? On simple facts, on accuracy, on completeness, as well as, in fact, precision, the versions that were fine-tuned but without question answer, but on the straight text, perform quite worse than the non-fine-tuned models. On the other hand, when we fine-tune based on question-answer pairs that we have generated from the extracted set, then you can see that the Mistral instruct version with the 7 billion parameters actually performs 6.7% better on simple fact question answers, improves accuracy by 3.7% versus the non-fine-tuned, the base Mistral model, increases completeness by 6.5%, and increases fact precision by 4.3%, and this is just after a single 8-hour fine-tuning process. Overall, therefore, we have come up with a number of lessons learned, let's say. First of all, that the structure and format of the training data matter significantly. So once you pass into the fine-tuning process question-answer pairs for a task that is question-answer basically requirement, you improve dramatically on the base model. Simple domain-specific, therefore, question-answer generation with the help of another large language model proves to be a practical strategy when the original dataset is not already in a training format. Fact-based evaluation metrics tailored to specific needs provide much clearer insights than generic scores. And finally, for the future work, we could explore extended training durations. As I said, we only let every fine-tuning run only run for 8 hours. It was also summertime. And we had some issues with overheating and the like, because we actually had the server as available to us physically in our desk, right, instead of having it in a rack in the IT department premises. We could use more refined dataset generation process strategies, and of course, we could try to use additional evaluation criteria to further improve performance and reliability in what appears to be a secure mission-driven setting like the ones that we have at the ESA. And with that, I'm going to finish. Thank you very much, and I would be happy to take any questions.
Thank you, Professor. Is there any quick questions before we move on to the next presentation? Okay. Given that we are back on time, if there are any questions, we can also discuss them at the end. We'll now proceed with Dr. Yanni from NCC Slovenia. Could you please share your screen? Try and share your screen. For some reason, I don't see any of the participants. He was here before. Maybe let's move on to the next one, and if it comes back, we can do that. Yanis, you want
Yes.
to go next? Thank you.
Okay, a bit early for me, but okay, I will manage.
Thank you.
So, just that I share my screen and run my presentation. A second. Compile, download. Open. Okay. There. Yeah. Okay, do you see my screen?
Yes.
Okay, good. So, okay. Oh, sorry, just something is bothering me here. Where is my Zoom? Okay, obviously. So, share. Up. Okay, so hopefully I'm not out of place here. I took this as an challenge to present application of an LLM, which is, I think, not exceedingly novel, but still many people don't know about it, and I didn't look into details how other people approach this. I know they did. So we'll be talking about steerable computer vision pipeline, which means LLM basically instructing, not with the code, but with, let's say, declarative kind of a language, what to do to solve our problem, okay? So I'm Yanis Perš from Faculty of Electrical Engineering. I work in the HPC area for about 3 or 4 years. Otherwise, I'm expert for computer vision. Not that much for LLMs, but I use them a lot. Oh, basically, what do we have in computer vision? We have basic situations where we need to quickly give out a prototype. This is in industrial projects, in projects, then when the questions come, you know, when you need to make a quick offer, there is a huge pressure that you provide the quote within, I don't know, a month or 2 weeks or something like this, and you have to quickly check whether what you're thinking you will doing is even possible. Okay, and here it is the idea: how do we trade a massive amount of computing power on a HPC, and we save on engineers, okay, and so people that would actually need to study the problem. So basically, we use large foundation models. We then connect them, and the sequence is of course fixed, but we make our LLM to actually set them up, to set the parameters, to set the queries, and so on. And then it drafts the simple text, which then it's read by computing pipeline. And this computing pipeline execute these models on an HPC with the strong GPUs, with a lot of computing power, and so on. So now, what are the foundation models? These are, let's say, holy grail, okay? Foundation models are very large pre-trained AI models, and every big AI company who wants to be like in the game has at least one. So these foundation models, like GPT's foundation model, okay? So then we have a lot of models in vision. Foundation means that they do on any task, like segmentation of image in patches for any task, whether you put in the situation of the production lines or you put in basically photo of the street. And there are a lot of tasks that they can do, and I will describe these later. So the idea of these models is that learn broad visual concepts. They know everything. So let's say they eaten everything in the world what is there to learn, yeah, about their particular task, about segmenting, about detecting object, anything. Now, this means they can be reused for any task. Like you suddenly get some idea, you get question from someone, hey, can you do this application? But you don't need to train them, yeah? So they're like general. The problem is they're very expensive to run, so they are fit for HPC or GPU nodes. All right, this is work very nicely, but still, they may use like 10 seconds, 20 seconds, 50 seconds per image, just to do some very basic thing that otherwise we could do it in optimized way in let's say different specialized model. Now, why they would help us to actually build working vision systems fast and check if the problem is solvable, yeah? And you will see the other role is, I talk about the other solution later. So one of the foundation models that we use, the first one is SAM2, maybe you know it, segment anything from Facebook. So it actually proposes high quality binary mask across the image. Now I don't have image here because I was struggling with the HPC node for about 2 hours now to get these images, but I can show the examples later if we have time. So basically it separates image to a different object, but it does not tell us what the object is. Yeah, so it can work on anything. So then the next model is CLIP. I think this is from OpenAI. And this is basically zero-shot classifier. So what does it mean? Basically, you ask him, it classifies the image patches with regarding to the strings, or you can make it. So it calculates the distance between the string goat is grazing. I have goats that I developed this thing for because it's so exotic stuff. I couldn't have any pre-trained model. So goat is grazing and then the actual image of the goat that is grazing. This is high-level stuff. It has been pre-trained again the whole world, and it gives you, for example, the cosine distance between this description and this patch, and you go through all the patches got from SAM2, and you can classify those which contain, I don't know, goat or something, spaceship or whatever. Yeah. So then this turns usually up with a lot of, let's say, decent number of false positives. And then the third thing that we do is, of course, we need a model that we ask basically and query him for a binary answer. Is there an animal here? So give him the patch. The patch said, okay, this is the goat, yeah, nothing else. And you say, okay, is there an animal here? And then he says, no. Then we throw it away. It was a false positive. Now, everything here is not 100%. It's a 90% if you're lucky, something like that. But the problem is that you need to program this each time anew. And this is, well, complicated task, right? So if you want to do every time. So what did we do? We actually put together that kind of a system where we have these all blocks here, these foundation models. Of course, we load them on a GPU. I test them with H100 or V100, and now I wanted to do it on NVIDIA A100. But the idea is that we have images or video, doesn't matter. Then we do some basic pre-processing, so something fixed. Yeah, we cut out the small place, like the region of interest. And then we run this SAM2. Then we do some filtering, very fixed filtering, no deep learning involved, like largest, smallest object that we expect. This is something that can be specified with very few parameters. Then we clip, yeah. So then we calculate the distances between our, let's say, objects we want to see, and then we do the verification. Now, this looks a bit complicated, but now we come to this steering via YAML, and I will first show the example. So this is a text that is generated by an LLM, and it has to be multimodal LLM. When we put in the, let's say, when we put in the image or few images, yeah, like I use ChatGPT for this, the thinking mode, and the sample, how this YAML should look like. And then it analyzes the images, and then what it does actually fills up these things. Now, this pre-processing is usually checked manually, it's not a problem. But then, for example, mask generator, this is SAM2, yeah. So, and it gives you some basically based on the image, gives you some parameters. This also are not that difficult. They can be also set manually if you're not very good idea. Okay, then some processing about the maximum size. But then we come to the thing then where and basically provides a number of labels that fit that exact image. Okay, so in our case, where I think I can basically show the images, so you will see what is. Okay, just a second. Yeah. Okay, we'll show it later. So it can see there are pictures of literally goat that I got for people who research farming at the Farming Institute of Slovenia, or let's say it could be here. These are the images now, and then actually it looks whole representation and put in something like this. It's going to be very long. And then for blip, it's basically just a question: is there animal in the image? Now, of course, with the searching animal, they would the LLM would put something else. If we put train, it would put, I don't know, or we would put cars. Yeah, is there a vehicle or something like that? Not original prompt. For verification, and then there is something. How do you set the results? How do you want to see the results? Okay, so this is this part that is also not that very complicated. Now, when we have this YAML file, you can see this is very simple format, so LLMs can master it. It's not that difficult. The key is that they use their multimodal abilities to actually see what is in the image and provide these hints. And what we can do then, sorry, well, the beginning here, which I went over. So basically, what I showed you now means we have pre-processing, very easy generation of masks. So where are the objects, but we don't know what object. Filtering, just some very similar, very easy rules, human-made. Then labeling, this is the problem, that LLM shines. Verification, few questions, which can ask, is this the verification, and then output, And we can run this a couple of times, iterate, tell the LLM, look, you didn't do it right. I'm getting tons of, I don't know, grass patches on the field, where I told you to only search for goats, and then it will reiterate it. So it's a quite fast iteration. Now, when we do this, we can take advantage of the multiprocessing. So once we have things done and we have 1,000 images to process, we can use the whole everything that is on HPC. So quickly from 1,000 images, we get in 1 hour maybe annotations or 1,000. And what is this good for is actually distillation. So, many production settings don't want HPC.
Jairus, we cannot see your slide.
Again?
Can you try again, please?
Yes. Okay, so sharing is not turned on again. So somebody has to allow to me. Somebody clicked something.
Let me see if I can do something. Can you try now, please?
Yeah, now I can.
Okay.
Yeah, thank you.
Sorry.
Tell me as soon as it goes away. So what is then the obvious benefit of this setup? In computer vision, many production settings want small models. Like YOLO here is the one. This is object detection, very popular. Don't need to go into details, which need the labels to be labeled. Okay, and our task was, for example, that we get from people from the Farming Institute of Slovenia. We want to detect all the goats and build the statistics where they're grazing. So if you look at the images, you cannot just go and scrap the whole web of images, but they had special kind of goats. So it wouldn't have sense for them to use months of scraping the internet and then manually annotating, because they had the data set. They have 10,000 images. So what we did, we basically run it through this pipeline. We got the results, which were about 90% correct. Of course, we took 1,000 images, we processed around 1,000 images. Then we remove all the images that had problems, and let's say we had 900. But those 900 were good, but we didn't annotate by hand. Now, we use this pipeline to export not the positions of the animals, but basically to actually write a data set. So this was here in the end, so for example, export YOLO, where basically we wanted to detect things. This is the sign that showed where is what kind of the grass and the goats. So and split and so on. So this pipeline with the proper code, which yeah, it was written, it's not that the LLM would do, I mean, not in this context, would then export the data set. And voila, you know, in a couple of hours or in a day, you have like 1,000 training images and like 5,000 cases of annotating objects. And now, why would you use it? Yeah, so rapid prototyping, batch curation. If you have, you know, of domain image, yeah, you have things in the domain. You don't have something scraped of the internet. Literally, somebody comes to you and said, "I have this problem. This problem is limited, but I have a ton of images. I don't have anybody to annotate them." Yeah, so of course it has to be moderate complexity, not something that the foundation models would break their teeth on, yeah, and you can basically make quite quickly the training set. Now, if you need real-time budget without installation, this wouldn't go. This is very slow. Let's say 1 minute per image, maybe 30 seconds, 20 seconds per image on the H100, I think, yeah. And if you have very fine-grained categories, this is, of course, a problem. Yeah, you cannot have like 10 different models of the cars. This won't work. It's good if you have goats versus a bucket and versus, I don't know, a sign. Yeah. And of course, if you have privacy constraints, you cannot use public LLM to use it for configuration. So at least some images have to go out into LLM if you want to do it. So now I will end up with the takeaway. So we have idea where we use actually the LLM as a domain expert, which configures our very rich foundation model pipeline, which runs very slowly in each HPC. We get the results out. Yeah, these results by themselves may be what we want, but if not, we can use it to actually train smaller models with this. So, and yeah, this would be it. Thank you. I can show something. I don't know now with all this mess here, how much time did I spend? Maybe I can show just the images and the on which I ran the stuff. So just a second.
Yeah, if you have images,
yeah.
Can I ask something while you're trying
yes.
to do that? The data annotation and so on. Do you have maybe some sort of an estimate how much time you saved from following your approach compared to doing it by hand, for example?
Yeah, very easily, because we used to do these things by hand. And we ended it like 3 years ago, but this would be, let's say, for that kind of the data set that was processed in 1 hour, it would be like 1 week person, or maybe 2 person weeks, okay? So something like that. And the HPC processes it. Now, of course, you need to iterate the prompting, yeah, because first result wouldn't be okay. Sorry, I'm just here. So first one wouldn't be okay, and then you would go to better one, and so let's see, goats. Okay, thank you. I have here the data. Okay, so do I share still?
Yes, we can still see your
Okay, so
screen.
this is I did it for other stuff, which I can show the results. I have some results for this too. So, for example, this is the case. This is what people came to me and said, okay, we want to detect these goats. You can see they're all, they could tell me they're all of the Boer variety. There is nothing else than grass, and you have this fence and so, and these signs. Okay, so then I can go and show you some results here too for some other cases that I tried to. So, okay, experimental data that we have. Okay, I think I have soccer tomato. No, okay. project zone. Yeah, okay. I won't be able to find them so far. So if you have any question, you're free to ask. Maybe while answering, I can maybe see where they have. Or let me see this. I can download them directly from the HPC where I have some old remnants of this code.
Are there any questions for Yanis? Okay.
No? Okay. Yeah.
Thank you, Yanis. Let's now proceed with the next presentation from Daniel Canedo from NCC Portugal. Daniel, are you here? Can you try and share your screen, please?
Yeah, sure. Can you guys hear me well?
Yes, we can hear you.
Okay, nice. Can you see my presentation?
Yes.
Okay, so hello everyone. Before I start, it's a pleasure to be here. Thank you for the invitation. My name is Daniel Canedo and I'm a researcher at University of Aveiro. And today I bring you a brief presentation about how to uncover archaeological sites from aerial imagery using vision transformers. So this is the outline of my presentation. I will start with the motivation for this work, the challenges that we faced, all the data engineering, the proposed system, the results that we obtained, and finally, future directions. So it's important to contextualize the technology that we use. We utilize vision transformers that are not large language models, but they utilize the principles of LLMs. So what this network essentially does is dividing the image into fixed size patches, and you can see these patches as words in a sentence, and the sentence being the whole image. And these patches have meaning within the image and also a position. And those two things are quite important for the transformer to learn all the relationships between all these patches during the training. So this work was done under the research project called Odyssey. And in this project, the main goal was to develop a platform for the archaeologists to use during their day-to-day work. And the work package that our team was working on was responsible for building a machine learning block for this platform so that the archaeologists could submit images and then this AI block would detect archaeological sites. And the archaeological site of interest for this work was the hill fort. And you can see here in this image what they look like. They are some kind of enclosures that do not have a defined shape, which complicates things for machine learning models to detect them. So some of the challenges that we faced, lack of publicly annotated data. So we had a lot of data, but they were not annotated. So we had to rely on the Atlas of Ilford in the UK, and we also had to rely on the knowledge of our archaeology team. This problem is prone to false positives due to the aerial perspective of the data. Since the perspective is top-down, we can only see the top part of the archaeological sites, and this top part is easily confused with any other element in the landscape. Not only for machine learning models, but also for the expert archaeologists that do these kinds of digital surveys. The data is quite heavy, which causes processing and storage challenges, and it's an emerging area in computer vision. It doesn't have many publications that we could inspire ourselves on. As for the data collection, our archaeology team did some LiDAR surveys here in Portugal, and we also collected some publicly available LiDAR datasets from Portugal, Spain, and the UK. The LiDAR data is essentially 3D point clouds, which are quite heavy on a computer. So what our team did was processing those point clouds to obtain a digital terrain model. That's what you see in the left side, which is already in 2 dimensions. Then we apply a visualization technique to obtain the local relief models. At the time, we did some state-of-the-art research and realized that this type of model was ideal for our case because it highlights micro topographies in the landscape, which makes it easier to detect anomalies in the landscape. And after having these local relief models, we essentially annotated the hill forts that we knew about. After having the annotations, we had to build our dataset. As you can see in this table, the images that we have access are quite huge, and we cannot simply feed those images to our models because, of course, it will give some kind of memory or GPU error. So we had to break these images down into smaller images, and we built a simple algorithm to do that. This algorithm essentially iterates over all the annotations, generates random coordinates for a cropping window, and the cropping is done if it respects 2 main criteria. The first criteria is that the archaeological sites must be fully visible within this cropping window, and the second criteria is that there should not be archaeological sites that were already previously saved in another iteration. So we want to retain uniqueness in the dataset. When we had our dataset ready, we could proceed with the training. The chosen model was called SimiX, which is a vision transformer. And this vision transformer is capable of fusing 2 types of data, RGB type with another type for semantic segmentation. This was ideal for our scenario because we wanted to replicate what the archaeologists already do in their work. When they do those digital surveys, they have in their monitor a lot of different types of data, and they search for the archaeological sites on those types of data because different types of data do have some advantages and disadvantages over the other ones. And in our case, we had our local relief models that highlights the micro topographies, but we didn't have the rich information from the satellite images. So our goal was to fuse these 2 type of complementary data. And then we proceeded with the training, and you can see the results of that training in the graph on the right. After having the model trained, we built our pipeline. We start with the local relief model tiles where we want to deploy our model. With a sliding window, we sweep through all those tiles. This sliding window has real-world coordinates. With those coordinates, we are able to do a web map service request to obtain the satellite image, and then we feed those 2 images on the model. Then the model produces some inferences that are filtered by a post-processing block to filter obvious false positives, and then we have our final inferences. After that, we do a human-in-the-loop process where we have our expert archaeologists to analyze those inferences and say, okay, this is an obvious true positive, this is a false positive, this I'm not so sure, and so on and so forth. And with that feedback, we are able to enrich our dataset with more images and retrain the model. So what we are essentially doing here is basically guiding the model in this difficult task of distinguishing between what is an actual archaeological site or another random element in the landscape that happens to have a similar shape. So this is the digital validation that our archaeologists do. I put here an example. We built a small script that presented our expert archaeologist with 2 images, and then he could analyze the inferences that are in those images. And just a curiosity, in this image, the left inference is a true positive, and in the right is a false positive. It's a football field according to our expert archaeologist. So as for the results, with this human-in-the-loop approach, we were able to reduce false positives by 99.3%. So we reduced it from 5.6K false positives to only 40 in Altumini with just one iteration of this human-in-the-loop approach. And these false positives, by the way, they are not they can actually be archaeological sites. We call them false positives because they are not annotated, so we consider them false positives, but they will be analyzed by the archaeologists to see if they are actually false positives or if there are something there. So we also discovered ill forts that were previously unknown to archaeologists, and the proposed solution at the time, which was 1 year ago, achieved state-of-the-art results. So the uncovered ill forts, we found 9 potential ill forts in Jerez and 768 potential ill forts in the UK. I say potential because they were digitally validated by the expert archaeologists in our team. However, they still require fieldwork validation to to confirm that they are actually ill forts. And in these images, you can see they are in the UK. The one that has a red dot is a known ill fort in the UK, but the other two are not known. But our team is almost certain that they are actually ill forts. As for the limitations of this approach, it has an high computational cost and long processing times. Processing data for the whole UK on a high-performance computer took around 30 days. The main bottleneck being the web map service requests, because we had to wait for the images to arrive. And also we could not make many requests because we could be timed out. Model fine-tuning is required when applying to regions with different site typologies. The model was firstly trained on Spanish and Portuguese data, and then when we wanted to apply the same model to the UK region, the performance dropped because the landscape in the UK is quite different, and even the ill forts are also a bit different from the ones we have here in Portugal and Spain. And the last point, we still require an expert archaeologist to validate the inferences from aerial imagery in that human-in-the-loop approach. This is a difficult task for the archaeologist because he has to validate thousands and thousands of inferences, but this step is crucial to obtain a good result because we still need this collaboration between human expertise and AI to improve the results. As for future directions, we want to explore archaeological predictive modeling to identify regions with higher archaeological potential. So instead of applying our vision system in the whole data, we want to focus on regions with higher potential. That would allow us to reduce the processing time. And also we want to explore visual foundation models. In these 3 images, you can see it's from a work that was published last month. It's quite recent, and they utilize the visual foundation models to detect archaeological sites. And as you can see, these models are able to provide a reasoning for why they detected what they detected. And also they do not require training, as the previous presenter said. And that's it for my presentation. If you have any suggestion for our future work that we expect to continue in the next year, or if you have any questions that I'm able to answer, go ahead.
Thank you, Daniel. Are there any questions from the audience? Yes.
Hi, Daniel. Can I ask you a question?
Sure.
You said as part of your workflow, when you do this cropping, okay, you try not to crop. You want the entire archaeological site to be in the crop, but also not duplicated in any other crops, right? How do you do this? How do you do this dropout of the duplicated crops?
Basically, we iterate over the annotations that we have, and then we generate coordinates, random coordinates, and we build a cropping window based on those coordinates. If that cropping window doesn't respect any of those two criteria that I mentioned, then we generate another set of coordinates, and so on and so forth until those two criteria are met. So you can imagine that this yellow window is like moving, trying to search for a position, ideal position to make the crop. And it does this to every single annotation that we have. And with that, we are able to retain uniqueness, because we don't want, obviously, to have duplicate annotations in our data set. I'm not sure if I answered your question or...
No, understood. Thank you.
Okay.
Are there any more questions? Okay. Thank you, Daniel, once again. Let's now move on with Spiros, and then after Spiros' presentation, we can finish up with Janice. All right.
So can you see my presentation?
Yes.
Are the presenter notes visible too, or my sharing?
No, but I think there are some Zoom tabs open and your presentation is not seen clearly. Can you try and minimize them?
Okay, is it better now?
Yes.
Okay. So good afternoon, everyone. I'm Spiros. I'm a research engineer here at the Cyprus Institute. I've been here for the past 2 years, and I've had the chance to work on a couple of consultations that focused on optical character recognition, or OCR. And our job was to explore how these new AI models can improve text extraction and document analysis. So let's first talk about, before we start talking about LLMs, let's look at how OCR tools perform today. So we have tools like AWS, Textract, and Tesseract, which excel at word recognition and character recognition, but only under ideal conditions, like clear structure, good resolution, clean printed text. But in real-world scenarios, we rarely have these ideal inputs. Usually documents can be complex, as in like tables, or they can be filled out forms. They can be noisy or low quality scans, some poorly printed, less than 200 dots per inch. They can be handwritten, multilingual. And in these cases, traditional model-based OCR, rule or model-based OCR systems start to fail by misreading or maybe misstructuring text. For example, an ID being transcribed by Tesseract leads to this example, which is not useful. So again, so this is what the typical OCR pipeline looks like. You start with an image, a scan, form, or a photo. You feed it into an OCR engine, and the system then will detect all the characters, recognize the word, and output them to you in plain text. So in essence, it's pretty straightforward. It's image in and text out. So an example would be this. Here's a real-world example. So this Starbucks receipt, which it's processed by Tesseract. So on the surface, it looks fine. The OCR picked up most of the text. It's readable, but it's making some mistakes. For example, V was transcribed into the yen symbol. Change do was changed to change Q, O bucks from S bucks, and some other spelling mistakes. And even the date has some format errors, which, I mean, when looking at the receipt as a human, you wouldn't have an issue. Even though it's faded, you wouldn't have an issue understanding what should be there. But for something like Tesseract, this is not the case. And if you have an automated system that depends on accurate transcriptions, these could be critical errors. So this is their key limitation. They can see the text, but they can't always understand. They cannot understand at all what it means or why it's there, for example. So when you integrate an LLM into the OCR pipeline, you essentially have a second step, a second stage, one that depends on language understanding. So the OCR still does what it does by giving you a transcription, but instead of stopping there, the text is passed to an LLM, which can add some contextual understanding before giving you the transcription in the end. So the model can, at this stage, reason about the structure, maybe correct some spelling or formatting errors. For example, okay, knowing that this is a Starbucks receipt and how the cup sizes, for example, are structured, it can fix the yen symbol into the VT, which I think stands for venti. You have the S bucks turn into the O bucks turned correctly into S bucks, which is a context-aware correction, which, I mean, it's not really a spelling mistake. And it can also fix some of the formatting issues and even correct the spelling. So now that you fix the transcription with the help of an LLM, you can also start doing a lot more with that text. The model doesn't just correct spelling or formatting, it actually understands what different pieces of text represent. For example, it can identify key entities, things like names, dates, total, and it can recognize how these fields relate to one another, like linking the total amount or the amount to a specific item on the receipt or an invoice. And here you can transform plain text into structured data, which is something that you can store, search through, or use in some other pipeline later on. So this step essentially is when the OCR output turns from just raw text into actually useful information. So this is what structured understanding, this is when that structural understanding becomes really useful. Like on the left, you have the cleaned up receipt that came out of the LLM beforehand, and you can prompt the model to go one step further and tell it to organize that text into a structured format like a JSON. It identifies what each part of the text means, the merchant, the date, the items purchased, the total, and the payment method. And instead of just a block of plain text, now you have data that's ready to be analyzed, essentially. And depending on the prompt, of course, you can fine-tune your output to exactly the way you want it to be. So far, everything we looked at still follows a two-step process. First, you have the OCR that reads the text, and then the LLM that interprets it. But this latest generation of multimodal LLMs, that separation begins to kind of disappear. These models can understand, can see an image, and also understand and transcribe it to you at the same time. So you have essentially recognition and comprehension done jointly by the same model. And because of that, they can also handle more complex layouts like tables and handwritten text more effectively than a traditional OCR system. They can also deal with noisy or low quality scans. And I mean, the biggest shift in this sense is that we no longer have a separate OCR engine and a post-processing step. You directly using one model, transcribe an image and produce structured and meaningful text output. So going back to our first example, suppose you used the Tesseract, the LLM enhanced pipeline. You could not use any model to fix this transcription because it's just fundamentally kind of useless. But using an actual VLLM, which has, we found at least, improved capabilities of text extraction, we can see that you can very easily transcribe this ID and turn it into very usable and actionable data. So we see that these multimodal LLMs are very efficient, are very good at OCR, but we can see how they can also handle information differently. So unlike OCR traditional OCR, which tries to read everything on the page, you can be selective with these models because they can understand the layout and the language, and you can also guide them with prompts. They can tell the difference between a handwritten number and a printed label and a checkbox, which makes them very effective with dealing with complex forms or mixed handwriting, where context and spatial relationship play a big role. For example, let's look at this tax return income form, where we can just use, in this case, I just used the ChatGPT. I gave it this prompt and nothing else, told it to extract the filer's name, social security number, and address. I also told it which format to give it to me, and essentially just gave me a JSON format of all the information that I asked for. And I double checked and it was all correct. Or I could ask it to just give me only the total amounts reported on this form. So it just gave me only the monetary data on this form. It's very important, though, to talk about what it takes to actually use these models in production. I mean, of course, there's a computational and cost overhead. LLMs require significant hardware resources, especially when dealing with a large database of documents. And even inference can introduce latency. So for large-scale digitalization projects, you need either access to very powerful on-premise infrastructure, or you can rely on commercial or cloud APIs, which of course are quite expensive if you use them over time. The second and major consideration is, of course, the accuracy and the rate of these hallucinations. The quality of the model's output depends very heavily on its size and the data it was trained on. Of course, we found that larger models generally perform better, but again, this ties back to the cost. And of course, sometimes the model can produce text that it looks right to you, but it actually isn't. It's wrong. So for let's say some high stakes document processing, like legal documents, maybe financial documents, or something like IDs, you still need, of course, some human validation step or some other automated verification mechanism in place so that these systems are kept in check. So they're going to speak. So to finish, I will talk to you about some of our case studies with using LLMs for document processing. So first case study was with a company here in Cyprus that specialized in offering software solutions, and they contacted us to help them benchmark some models against the Tesseract using their real-world document datasets. So their issues were with poorly scanned text and handwritten samples, and also some layout issues with when processing document forms. We ran this benchmarking and we found, clear advantages in all of in layout understanding and the way it structured its output, and the accessibility, like cloud versus hosting something yourself. And this also led to a recommendation from us for maybe a hybrid OCR plus LLM pipeline, and also some further testing with proprietary data. Our second case study was with the Ministry of Defense, where our goal was to essentially do a consultation / feasibility study on using self-hosted VLLMs for transcribing a very large database of Greek handwritten manuscripts, which some dated back from decades, from the 60s. So the challenge in this case was handwriting variability. Some documents were quite easy to transcribe, some featured some cursive, and some featured very heavy cursive, and also some age-related quality degradation on the pages. And in this case, we explored self-hosted visual language models. We explored Gemma, Quen, and Llama Vision, while also testing the performance of a very large model like ChatGPT. We evaluated 105 documents, dividing them into these 3 difficulty categories: easy, medium, and hard. And you can see the results here. We used the character error rate as our metric for the accuracy, and you can see that most models, even ChatGPT, begins to kind of fail at the medium difficulty. Its accuracy becomes not so good. So we found that all general models have this with Greek data. With English data, this is not the case. And this consultation again concluded that there is a need to fine-tune on domain-specific data. And that's all I have on my end.
Thank you, Spiros. Are there any questions for Spiros? Okay. Now let's move on to the final presenter before we conclude the session. Gianni, do you want to share your screen?
Yes. Okay, can you see my screen?
Yes.
Okay. So thank you. I'm sorry I was late. My clock was still 1 hour behind. So let me start with the presentation for intelligent agents and large language models for modern cyber defense. So the key challenge we address is that the most cybersecurity datasets are static and they quickly become outdated, which limits their ability of artificial intelligence systems to learn and adapt to the new types of the attack. So our vision is to transform these static datasets to dynamic interactive simulations where intelligent agents and large language models can evolve, interact, and also learn in the real time. So it's like very similar how attackers and defenders do in the real life. The motivation behind this lies in the growing complexity of the modern cyber threats. So attacks like social engineering, phishing, and ransomware are constantly changing their strategies, and they're also exploiting human factors, which often outpaces the capability of traditional rule-based systems. So, as mentioned before, cyber threats are becoming smarter, faster, and also far more coordinated than before. So attackers don't just rely on technical exploits, they also target the human factor using manipulation, deception, and psychological pressure to gain access to the systems. Meanwhile, most existing defense systems remain static and rule-based, and they only react when the attack already happened. So to keep pace with this changing landscape, most of the modern cybersecurity must evolve. So they need to be adaptive, data-driven, and context-aware, and also capable of learning from new threats in real time, rather than just rely on the fixed patterns or signatures. So intelligent agents, they're like autonomous systems capable of perceiving their environment, making decisions, and also take actions to achieve specific goals. They operate through like a continuous loop. So first is the perception, then decision, action, and learning. This is like a continuous loop, which they do continuously. This allows them to improve their performance over time based on the experience they gained. Now, these agents, they're already used widely in robotics, finance, and healthcare, and they're also used now in cyber defense to automate or to optimize some decision-making tasks. Specifically in cyber defense, they enable us to simulate and safely test high-risk scenarios like attacks and defenses without putting some real systems or data at risk. Now we move to large language models. So, as mentioned before, they're like transformer-based systems which are trained or on a very big amount of text and data. So they're capable of understanding and summarizing and, of course, generating human language with remarkable fluency, which allows them to mimic human interaction. I won't name the chatbots because they're like mentioned before, but these are like the main that are used. So how to combine all of this? So when we combine agents with large language models, we create something like adaptive, context-aware cyber systems which are capable of learning and reacting like human counterparts. In our setup, attacker engines generate realistic phishing or social engineering messages, which simulates on how real attackers would start the communication. On the other side, the defenders, defender agents, they analyze, classify, and then respond to these messages. They use either traditional machine learning approaches or large language model-based systems to detect deception and to prevent it. This interaction enables human-in-the-loop training, where these analysts can observe, adjust, and learn from these scenarios in some safe environment. Together, these three elements, they form like a foundation for proactive and autonomous cyber defense system, which is capable of anticipating threats rather than just reacting to them. What we did with my coworkers, we are still doing it actually. It's a big project, so we are doing a synthetic simulator to test and to evaluate intelligence agents safely, where we are developing a synthetic simulator that turns static cybersecurity test datasets into a dynamic interactive environment. So this simulator consists of 4 main layers. So the first one is data management layer, which handles the loading and normalization of dataset features. Next, we have simulation layer. This layer visualizes a network of nodes where each node represents its own data value and security level. Then we have the agent layer, which defines how the attacker and defender agents behave and interact within the same network. And then at the end, we have the visualization and control layer, which allows us to monitor and metrics and show us the network states and the success rate of attackers and defenders in real time. Maybe it's better if I show you the pictures. So this is the dataset operation. So at this point, we take a static dataset. This one is for ransomware. I will tell more about this later. So we take a static dataset and we can extract features from the same dataset. As you can see in the tabs, we have also feature engineering. So feature engineering can also extract features and also select features, meaning we can reduce the set of features. The goal of this is that we can make this dynamic dataset reusable so that agents can learn and adapt rather than just simply analyze the fixed samples. The last page, you can see it's synthetic data. This means that from the static dataset and those features, the program software can generate unlimited amount of synthetic data based on this data. Next is the visual pipeline. So this is like how data flows. So we can see that it begins with dataset preparation. So we can either load dataset from a file, or we can use a synthetic data generator where we then normalize and then we do some actions. For example, if we have agents in the middle, they can have different algorithms that are. For now, we have like 4 implemented random forest, support vector machines, logistic regression, and neural networks. In the future, we are planning to implement more. And after that, when we run the simulation, we can do some analysis and we can learn from this. Okay, maybe this picture is better to understand. So we have the simulation environment. So like I said before, we have a network of nodes. Each node represents a user or a system. I will explain later what each system means, like these letters. But from this photo, you can see that we have one attacker and one defender. In the future, we will also have multiple attackers and multiple defenders. The green ones are systems that are safe, and the red ones are the systems that are comprised. And then the defender agent, he chooses the action, how he will proceed with the appropriate action for this node. So it can either isolate it or something else. Okay, so we have two case studies. So the first one is ransomware. This is also the simulation environment picture from before. So we have like static ransomware dataset, and we extract features like PA headers, structures, and binary metadata. They're then mapped onto the network, where each node has its own level and security level and data value. So this picture shows the first version of the program. Now we have the third version, but I didn't include it yet because it's still in progress. So we compare data-driven agents with random agents, where the attacker uses algorithms to estimate some probability of successful breach, where they only select targets based on data patterns rather than just random choice. On the other hand, the defender agents, they patrol the network and attempt to counter some ongoing attacks, where they create like adaptive interactive setting to observe some attack defense dynamics. Okay, so now for the letters, so we have different systems. So letter S means server, letter W means workstation, letter R means resource, letter IDS means intrusion detection systems, and we also don't have IPS, means intrusion prevention system. So we are expanding this network. Okay, now if you go to the second case study, the second case study was about phishing and social engineering attacks. These are like the most common and effective forms of cyber attacks. Our developed simulation models are realistic interaction between the attacker and the defender, where each of them are regarded as agents. Of course, this simulation is run in a controlled environment. The attacker generates some convincing phishing messages based on data sets that we selected. I will say later why we couldn't generate them, but the data sets are from real-world messages that were gathered together. On the other hand, the defender agents, they analyze the messages received, and then they classify it as malicious or safe. For the defender agent, we used two sets of approaches. So one is a classical machine approach, logistic regression, and term frequency, inverse document frequency features. And the other part was using large language models. This is mainly because they can understand the context, tone, and they can see the linguistic differences within the messages. Now, the problem here is that the ChatGPT and similar ones, they do not allow us to generate attacking messages. So this is also one good point to develop our own large language models. Also, on the other hand, we used rather small large language models. So it's like 1 to 7 billion parameters. So also the results are not so good as the classical ones. It's like a couple of percentage difference. But also, as in previous presentation, there was mentioned that it's better to fine-tune the model to the field that we have. So this is also one of our future work that we will fine-tune on the cybersecurity field, and also to improve the efficiency of these agents. Now for the conclusion, our work shows some intelligent agent-based simulations that can safely replicate some of the real cyber attacks and defense dynamics. This simulator connects these static datasets with dynamic evolving environments, which is one of the crucial steps toward the adaptive cybersecurity systems. In the first study, we noticed that data-driven agents demonstrated strong adaptability and decision-making, but this approach remains limited by the model simplicity and how the data is structured. In the second case study, we added agents that are using large language models. This is mostly because of the contextual understanding and to be more realistic. As I said before, since we used smaller large language models, the detection and reasoning capabilities were still limited. If I can conclude this with overall opinion, so combining all of these before mentioned techniques, we laid some groundwork for some proactive, expandable, and adaptive cyber defense system, as well as possible training environment for both artificial intelligence and human defenders. Okay, this is all from my side. Thank you for listening, and if you have any questions, feel free to ask.
Thank you, Gianni. Are there any questions? I can just make one and then we can conclude. On the, you said earlier that the attacker messages weren't allowed to sort of create them using LLMs like ChatGPT and so on. Will you have the same issues if you use local LLMs, for example, or will that not make any difference?
It's the same with local large language models, because I used Olama, and let me just check. We used Llama 2, Llama 3, Yema, P4, Moondream, and Mistral. So,
okay, so it's not like any red flags from the company itself, it's just the LLM.
Yeah. LLM,
okay.
Yeah. They don't allow it because of the moral and ethical constraints.
Okay. All right. If there are any questions, I would like to thank you all, and let's conclude this session. I again apologize for the rude interruption. Yeah, I hope you find this interesting and helpful, and we'll see you at the next one. Yeah. Thank you, guys.
Thank you.
Thank you.
Bye.
Thank you.